Okay, hello class, Physics 15. So we're going to have a talk here about chapter 2. We're going to be talking about speed, velocity, acceleration. These are all things you're familiar with. That's good news, right? We've all gotten on a bicycle and you're still, then you accelerate up to a speed, then you're riding down the road, or the same thing in a car. You're parked, then you accelerate up the road speed, and now you have a constant velocity, then you decelerate, you stop, right? The difference is in physics, we quantify it, we measure it very carefully, and we use math. And with math, we can make predictions, and we can say, well, if you were going at this velocity, and then you accelerate it for this amount of time, then we can calculate the distance and stuff like that. So we're going to go ahead and do that right now. We're going to start into that. All right, let me move my camera here. I'm a little bit old school with how I do it, but that's okay. It will be fine. We'll all be good. Focus in. Yeah, I like using the video camera. I think it works better, or it has some advantages over. What was that? There we go. Over just using the camera in the computer, which is a much smaller camera. Okay, we're just about there. So chapter 2, describing motion. This PowerPoint is in your, there's a link to it in the Canvas for this class, so we'll be all set. Okay. Chapter 2, describing motion. PowerPoint. Yeah, let's begin. So Newton, right? Newton was a scientist. He was a genius. He was hiding out on a farm in England during the plague, right? They did social distancing. They literally did that. They knew that there was a plague. The big cities, people were dying, so he just went to his farm and he stayed there for a couple of years or whatever. He was already self-taught in math. He had gotten books from various places, but Newton invented lots of things. If there's ever been a role model for use your time productively when you're social distancing during some kind of coronavirus, he is that role model, right? He is that person, so it's fitting. Okay, to see well, we must stand on the shoulders of giants. Yes, I'm a professor, but I'm for the most part just telling you what these other folks have discovered, right? Okay, first things first. We must provide clear definition of terms. Yes, in science we are very precise and clear on things. When we're in our car driving around, yeah, we don't want to speed, so we have to look at our speed limit. But in science, we do things even more precisely, right? Okay, the meanings of some terms are different in science than in our normal language, right? We all know that the word theory, when we say the theory of evolution, well, theory is used much more strongly in science than in our common vernacular. When you say, oh, it's just a theory in normal discourse, it's a weak thing, but in science, a theory there's actually quite a bit of evidence, right? So it's used. Well, there's other words that have a different meaning in science. Okay. Yeah. So precise definitions. Well, so average speed and instantaneous speed, right? We know that if you drove 100 miles at 100 miles an hour, right, you'd get there in an hour, but you weren't going 100 miles the whole time. You were going maybe 120 at some point. I mean, don't drive this fast, right? This would be like this guy in a race car. Then you're going slower at some point in the curves, right? But your average speed. But instantaneous speed, that's what's on your speedometer. Actually, it's not instantaneous. It measures it over a very small distance, right? It measures the rotation. So there is a little bit of distance that it's measuring it over, but it's a very small distance. So your speedometer has the instantaneous speed. Velocity. Velocity has a very specific meaning in physics. Not only is there speed, how your distance per time, right, miles per hour, but velocity has a direction. That's very important. We're going to see that, right? If you have two boats, and they both have, you know, motorboats, if they're going this way, well, they're going to push each other. So they're going to, their force is going to add. If they're going like this, two boats, well now they're not going to go up this way. They're kind of going to go this way, right? If they're opposing each other, well, the boat with the stronger motor is going to win. So that's where direction. It's a distinction that we make, and it's very important, and that will become very apparent as we get through this course, right? And then acceleration. Acceleration, of course, is you're going at a speed and then you step on the gas. There's also negative acceleration, deceleration when you put on the brakes, and then you're slowing down, right? You can feel it. We can feel acceleration and deceleration. Speed. Yeah, how fast? Yeah, this PowerPoint this isn't written quite well. Changes its location, right? So speed, you are moving in a distance, right? You're moving, you're driving to school, you're driving to the grocery store, you're traveling distance, right? And then divided by some time. You know, typically you're driving around town, you should be going about 30 miles an hour, right? So units of speed. Now, miles per hour, meters per second, right? In this class we use miles and meters. You want to get a handle on that. Those of you that have traveled, folks from Canada, folks from the rest of the world, actually, except for the United States and a couple other small countries, all use the metric system. We use the metric system quite a bit in science, so you just got to learn it. Kilometers per hour, inches per minute, right? Average speed. Okay, we just talked about that. Yeah, distance traveled over the amount of time. If you traveled 60 miles and it took you 1 hour, well, your average speed was 60 miles an hour, but maybe you're going 70 at one point, you know, certainly in town, hopefully you're going slower. So that would be an average speed. A distance, miles per hour, distance over time. It's a mathematical equation. You're dividing distance by time. Units are important. If someone says, oh, you know, first I was going 60 miles an hour and then later on I was going 50 kilometers an hour, how fast was I going? Well, you have to convert. You can't do that equation. You have to convert either everything to miles or everything to kilometers. You have to use the same units, right? So here's just, right, a kilometer is smaller than a mile. So it's 0.62 of a mile. Or a mile is bigger than a kilometer. It's 1.609 of a kilometer, right? So if you were going to convert, you would do 0.621 miles over is equal to 1 kilometer, right? So it's a ratio. So 70 kilometers per hour, you would use this, and then 70 times 0.62, right? Miles per hour. Notice what happened here. The kilometers canceled out. That's units. I'm going to be talking about units this whole class. You never write just numbers in physics. You always write number of what. So there's always units. It's 70 kilometers, 0.62 miles, right? Here it's 70 times 0.62 miles per hour, right? And in the back of your book, in the appendix, there are conversions for many type things, not just miles, but there's also conversions for weight and other things. So you always want to look through the appendix when you get a new book. A lot of good stuff there. All right, so here's just a good example. So if you have 70 kilometers per hour, right? So you want to convert 70 kilometers per hour to meters per second, right? So you know that, so kilometers per hour, you just write it as it is. You know that 1 kilometer, K is for 1,000, is equal to 1,000 meters. But you set it up so that your kilometers are on the bottom. Look what happens. Your kilometers cancel out. 70 times 1,000. And all that's left, the kilometers canceled out. You have meters per hour. Now you want to convert the hour into seconds, because that was the problem, right? So once again, here's your answer from when you did the first conversion, 70,000 meters per hour. Now 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. Notice the minutes cancel out. This is units. Your hours cancel out, and we're gonna practice this. Don't worry when we get homework. So for a lot of you, if you're seeing this for the first time, you're going to be doing problems, and you're going to get practice doing this, right? You don't watch a film on basketball, then you know how to play basketball. You actually have to get on a court. Well, that's problems in physics. You got to work on the problems, right? So then you would have 70,000 meters versus this many seconds, right? And now you have 19.4 meters per second. Trust me, you're going to get practice on that. Okay, average speed, we talked about that, right? If you went from Kingman to Flagstaff, Arizona, and you traveled this 120 miles, it took you 2.4 hours. And then this section, it was 140 miles, it took you 2.6 hours, right? Right, so the total trip time, you add up your time and how much time it took, and your average speed was going to be 52 miles per hour, right? Okay. And let's go, we can move on. Okay, rate. Yeah, we talked about instantaneous speed. Instantaneous speed, that's what's on your speedometer. Also, if the police have a radar gun, they're able to measure. Now, your car did move. The radar goes out and it bounces off and it comes back to the detector. So there's movement, but it's over a very short distance. So it's instantaneous. It's not quite instantaneous, but it's really darn short, right? It's a more precise wording. So it's the rate at which distance is being converted. Okay. And what does a car speedometer measure? We already went over that. B, instantaneous speed, right? Okay, enough about that. And enough about this. We talked about that. Okay, velocity. Velocity involves direction, right? In science, things are done precisely. So here we care about not only the speed, right? Your speedometer doesn't know what direction you're going. It's just measuring 50 miles an hour. It doesn't know if you're going on a curve, right? Or if you're going straight. Velocity, that matters, right? When you're going in a straight line, it's important when you're driving, right? Keep your hands on the wheel, drive in a straight line, right? So velocity, the direction matters. And I gave you the boat example. It's a vector. Okay, vector is probably a new word for a lot of you. So when there's acceleration or velocity in a direction, and you care about the direction, now it's a vector, and you have to keep the direction. You have to keep that in account. You're worried if you change your direction, you've changed things, right? So the vector quantity, you're always worried about the direction. They have a magnitude. Magnitude would be like in a car, it would be your speed in the direction. You're going north on Highway 101, right? So a change in velocity can be a change in the object's speed or direction. This is, we're in common language, we're kind of used to using velocity and speed interchangeably. In science and physics, you don't. You can't do that. In science, if you're talking about velocity and if you change the direction, that matters, right? Okay, a car goes around a curve at a constant speed. Is the car's velocity changing? Okay, at position A, the car has, the answer is yes. The velocity is changing, even though the speed may stay the same. Even though the speed may stay the same, in physics, if the direction is changing, then we say that the velocity is changing. Okay, it's just the way it is. When I was in physics class, I was like, what? The velocity is the same. No, it's just think of it as a new word. Velocity is a different word in physics. And so if the direction changes, and the speed stays the same, it's changing, okay? And here what's happening is that there's actually friction, there's a force, right? Like if it was slippery, if it was ice, we see these YouTube videos, for those of us in California who maybe don't ride on snow a lot, you see these YouTube videos of cars skidding off. Well, when you're making a curve on a dry road, there's actually a force. It's the force of friction of the tires on the road. So that is a force that's acting on the car, or that the car is imparting that force on the pavement, right? So there's forces involved. So yeah, this is a change of velocity, even though it may be the same speed, the velocity has changed. So okay, it's a definition. So yeah, and we talked about instantaneous velocity. But instantaneous velocity, again, other than instantaneous speed, the arrows matter. So here you have a car going in 10 meters per second. Graphically, quite often they use diagrams. You'll make the arrows longer. So 20 meters per second shows that this car is going faster than that car over there. And the arrow is also showing the direction. So it's a velocity. Okay, so we're going to move on. Acceleration, right? Not that anyone here ever does quick acceleration, but you're in your car and you put it in gear and you start to go, right? Well, you accelerate. So you go from 0 up to 30 miles an hour. You're cruising in the city. Then you go to get on a highway. You get on the ramp and you accelerate up to 65 miles an hour, right? You can feel that. You can feel the acceleration. Also, if you brake, a deceleration, you can feel the braking, right? So yeah, we don't see velocity, right? When I was a kid, we would ride in the back seat of my dad's car. Me and my brother would be throwing things at each other. If it's velocity, you can toss a ball to each other. But if it was acceleration, well, then the ball would go back and hit the seat, right? So you can feel the acceleration. So most of this, a lot of this you already know, right? Right? If you're in an elevator, you can feel like, or if you go to an amusement park and you're in one of those things where, like a roller coaster or whatever, those things where the bottom just drops and you fall, right? You can feel that. Yeah, and again, acceleration is a vector quantity. The direction matters, right? And this little direction, the direction of the acceleration vector is that of a change in velocity. This triangle thing, that's the Greek letter delta, and it's used in science whenever there's a change. And then V is for velocity, so a change in velocity. So when you write this little triangle, it means a change. It's delta. Yeah, and then in science, a decrease in velocity, a slowing down, a deceleration. In science, if you do the math, it's just going to have a negative sign, so it'll be like a negative acceleration. So. Okay, so here these cars are all going in the same direction, right? And okay, so here he's going at 8 meters per second. Then there's a delta, a change in velocity of 12 meters per second. So you just add it. So he's going at this initial speed, and we're going to be doing a calculation that does just this. Math is amazing. You can predict real world things with math. It's kind of scary how our universe is mathematical. It's really kind of scary, spooky. It's neat. I like it. So if the car is going 8 meters per second, and then you increase your speed by 12 meters per second, well, now you're going 20 meters per second. So you were at 8, you've increased it by 12, now you're going 20. That's good, right? That doesn't seem too hard, so that's good news. The velocity is increasing. The acceleration is in the same direction as velocity here. Okay, now what happens if you're going 20 meters per second and then your change of velocity goes down? It's a minus 12 meters per second. Well, you add them again, right? 20 plus a minus 12, right? Algebra is going to give you 8 meters per second. So now this is where the graphics kind of show. You would have a vector representing 20. You added 12, but it's going in the other direction, minus. Your resultant is the difference between the two. And so you've had a negative acceleration. We would call that a deceleration in common language, right? Now acceleration also happens because there's a change of direction. Again, if you're on the curve, even if your speed hasn't changed, in science it's a change in velocity. And it's interesting how they do it. So here you have this car is represented by this arrow going in that direction. This car is represented, or here it's showing the same car. Now it's going in this direction. The delta V, the change in velocity, is the difference between the two. Although in this case, it's just a change in direction. That's gonna make a lot more sense as we get into this class. Okay. Yeah, and if a car is on a curve like this, that would be a big circle, right? The change of velocity is towards the center. So it's at right angles to the velocity. Yeah, then average acceleration, so now math, right? We are doing math, and boy, are you going to be doing some math. So here, yay, we're doing math, right? So acceleration, a change in velocity over time. So remember the delta V, that's the Greek letter delta V, means a change in velocity over time. Well, this makes sense. If you were at zero, and then sometime later you're going at 30 miles per hour, well, your delta V is 30 miles per hour. And then if it took you 20 seconds to do that, that would be your acceleration. It didn't take long for the math to start. And guess what? We do math from henceforth and forever. And velocity is distance divided by time. We know that, like miles per hour is distance over time. Now the units of acceleration are velocity by units of time. Yeah, so acceleration, if you're going 20 meters per second, right? And you did that, and you did that for 5 seconds, right? It changed for 5 seconds. Well, now 20 divided by 5 is 4 meters per second per second. Meters per second per second. So that seems kind of strange, but remember that if you have, let me do a quick illustration. Remember from algebra, just so that we get this, right? Remember from algebra that if you have, 1 over a fraction, right? 1 over a fraction in your denominator, then that's the same as if you inverted your denominator, and now it would be seconds per meter, right? So remember that. Yeah, you have to know algebra for this class, right? So that's all you're seeing here. That's how they did that. So in case you're scratching your head, you're right. You might be a little rusty in your algebra. That's all that happened here. Okay. Yeah, so a car starting from rest accelerates to a velocity of 20 meters per second due east in a time of 5 seconds. So it was at 0, and then this is your final velocity, and it took you 5 seconds for that change, or at least you care about this 5 seconds for some reason. That's the 5 seconds you're worried about, right? So the acceleration was 4 meters. Now since it's 4 meters per second, and then remember in the previous one, where we did this, well now, so it's going to be meters per second squared. Instead of saying the meters second per second, it's going to be meters per second squared. Okay? It's much more needed. So the units for acceleration are typically a distance over time squared, meters per second squared, as opposed to velocity, where this would just be meters per second. Okay? And that's how that happened. So. And then instantaneous acceleration, again, it would be over a very short period of time. So, yeah, now here they're just showing, so here's a toy race car, right? A little slot car. When I was a kid, we had Hot Wheels. We just pushed them. That was our, or we would use ramps and use gravity. That was the way we got motion going, right? Back in the old days. Okay, so here they're showing if you got this toy car, and over 35 seconds, it starts, you know, the position was 0, but after 35 seconds, it traveled 18 centimeters, right? Okay, so here is an interesting graph. We're going to go through this. What it's showing, here you have distance, centimeters. So here you have a toy car, right? And you have a distance of perhaps, oops, not showing up, 30 centimeters. Over time. So we're going to analyze what is this doing, right? We graph a lot in science, so we're just going to start getting used to. So it starts off, well, let me put some of these here, otherwise I'll just be repeating it. So each interval on an axis represented a fixed quantity of distance, right? So here's distance and time is here. The first data point, okay, so nothing's happening, right? It's 0 seconds, 0 centimeters. The second data point is at 5 seconds, and it did a distance of 4.1 centimeters, and then etc., right, as we move along the graph. Okay, when is the car moving the fastest? Well, here, notice what's happening. Its distance has changed, well, not quite, 20 centimeters, and what is that? Maybe 19 seconds? What's happening here? So here, time keeps going, right? We can't stop time. We can stop traveling a distance, though, but the distance isn't changing. So here, the toy car is standing still. There's no motion. Here, it's moving again. Distance is changing over time, but notice here the distance is not changing as quickly. Here, the distance changed quicker over a period of time. Here, what's called the slope, it's more gentle, so it's going slower here. What's happening here? Here, your distance actually decreased, so the car's going backwards here. Okay, so graphing, right? You gotta just be good at graphing. The way you get good at graphing is, well, you look at a lot of graphs and practice, right? Okay, in the opposite direction. Yeah, so it starts moving in the opposite direction. What is that here? Sometime between 40 and 60, right? Yeah, so slope is, they say rise over the run. Well, the rise here just means, you know, the vertical side of the graph. The run is your horizontal side of the graph. So here your rise over your run is sharper. There's a higher rise over the run for this section than here. So here your distance over time is changing quicker, right? So it's a higher velocity. They call that the slope in mathematical terms, and I'm sure you've seen it in algebra. Yeah, and the slope is 0 here between 20 and 30 seconds, right? That's what that is. And negative, so between 50 and 60 seconds, you're going backwards. All right, let's move on for a bit. We do a lot. Okay, let's do this one. Now we're going to change this up. So what this is now, we have velocity on this side, and we still have time on this side. So before we were changing distance over time. Now we're changing velocity. So velocity is you're already in your car cruising. You're already cruising. What can you do? You can either step on the gas and speed up, or you can hit the brakes and slow down, right? So you're changing your velocity. A change in velocity is acceleration, right? So here our velocity is going to be changing over time. So the velocity is constant whenever the slope is constant. So here we're just cruising around. What is that? That would be about 9 centimeters per second. We're just cruising. Then here, look what happens. The toy car slows all the way down to 0. So the toy car slowed down and stopped here for some period of time. Then here the toy car sped up again, so this is the acceleration part. Now here, it's just going at a constant velocity of 0.5, right? And then here it changes, the velocity changes, and it's actually gone negative, right? So the velocity is negative. All right. So that's enough of that, right? So we want to let me move on from these graphs. We do a lot of graphs here. I think we did enough to we did enough to get a handle on it. Okay, so now here's something we can all identify with, right? Someone is they're in a race. So the 100-meter dash, right? A lot of schools, you've seen it on the Olympics, they get up and they sprint 100 meters, right? So when they're first starting, they're kind of, they're at zero, they're just at the starting blocks. Then, right, go. So they have to, so here they're saying speed, because maybe they're wobbling a bit. Okay, so he accelerates, right? He's going fast, but then eventually he's not accelerating anymore. He's just running as fast as he can, but he or she, the person has hit their stride, and they're just running. So there's no more acceleration here. Now they're just running as fast as they can until they hit the finish line, right? So there's an increase, there's a constant acceleration where you're going fast, and then you're going into your stride, which is just your normal speed. So your acceleration is decreasing. It doesn't mean your velocity decreased. It means that your change in velocity has decreased, and now you're just running at a constant velocity, albeit quite fast. Okay, so the thing is, right, read the book, watch this video, do the math. That's why we do it again, and we do it again. And also this PowerPoint is going to be online, right? That's how you learn. You don't just go outside, shoot one basket, and okay, well, I kind of figured that out. No, you got to keep shooting baskets if you're going to get any good at foul shooting, right? So, sorry, physics is the same way, right? Yeah, the greatest acceleration is at the beginning of the race. For the remaining portion of the race, the runner continues at a constant speed up here. So the acceleration is 0 up at this part, right? So this is speed, meters per second, versus time, and your speed is changing, and that's called acceleration. All right, I think we've done enough graphs. We're going to talk now uniform acceleration. It's not in your car where you're kind of accelerating and slowing down, accelerating. Uniform acceleration is where you kind of step on a gas pedal, but you're going. This is a very unique form of acceleration, but we're going to be doing this because the math is